Sardar, and it's Math Physics 2212, Lab 4, Ball Magnets. Today we'll go over Introduction, Models, Experiment Code, Discussion, and Conclusion. The purpose of this lab is to experiment with ball magnets to determine a magnetic dipole moment and distance relation to magnitude of the magnetic field, as well as to simulate magnetic fields on and off axis of a ball magnet using the Biot-Savart law and compare values with experimental data. Our fundamental physics principles is Biot-Savart's law, which says that the magnetic field of a constant current is based on the direction of current, length of a wire, and distance to some observation location. And this will be used to find the magnetic field of a dipole via a ball magnet. Here we have Biot-Savart's law, where mu naught is the magnetic constant, the magnetic field of a ball magnet, where k is a value of constant values, and it can also be rewritten using natural logs. We also have the Biot-Savart dipole general form, perpendicular form, and parallel form. Here is our results preview, where you can see the magnetic fields at different locations, as well as the magnitude of the magnetic moment and the B net at a certain location, 45 degrees. Some assumptions we have is the ball magnet ideally acts like a magnetic dipole, magnetic field in the z direction is ignored, and external forces are negligible except for Earth magnetic field. Our materials consist of the phone, the magnetometer, which is part of the system, the ball magnet, and Earth, which are part of the surroundings. First, we determine the position on the phone where the magnetometer reads the magnetic field. Next, we measure distances for different magnetic fields on axis parallel. And then we measure the magnetic field off axis at a 45-degree angle. On the left of our data collection, you can see at different distances the magnetic fields on the parallel axis. On the right, we graph the correlation between the natural log of the magnetic fields and the distances. And then on the bottom, we calculate the net magnetic field on a 45-degree angle. And in our y direction, we account for Earth's magnetic field by aligning it with the y direction. In our observations, we can sum it up to say that as we move farther away from the magnetic field decreases, as we move closer, it increases. For our calculations, we solve for the magnetic moment of the dipole, and we use our k value as determined by the equation, as well as a r value from our data to get a magnetic moment of 1.627 amperes meters squared. Moving on to our code, we start by making a function to determine the magnetic field due to the dipole, as well as making observation locations on axis and perpendicular axis to the ball magnet. Next, we find the magnetic fields and place arrows at the different observation locations on axis and perpendicular axis, as well as solving for the magnetic field at a 45-degree angle from the ball magnet. For our code results, we can see the magnetic fields at the different locations where the orange ones are on axis are in the direction of the ball magnet, and the blues are perpendicular and are in the opposite direction and half the size. Whereas the purple one at a 45-degree angle is also an angle, and we can see the B net at that location. Similarities in our discussion are limited to as we get farther distances, the magnetic field decreases. Some differences in our experiment, we saw a 6.00248 E negative -05 Teslas at the 45-degree angle for magnetic field, whereas the code was 1.359 E negative -06 Teslas. In the simulation has ideal circumstances, completely ignoring the Z, whereas the experiment can't. Some sources of error include that electronic devices nearby could have affected the magnetic field, and location of the magnetometer was inaccurate. For discussion questions, if we did not orient our experiment with the Earth's magnetic field by not compensating the magnetic field in the x direction, it would be affected instead of solely the y, causing for issue in correcting the fields to account for Earth's magnetic field, and all values would become inaccurate. And if we were to stick two identical magnets together end to end and run the experiment, the magnitude of the fields will double, whereas the direction will stay the same. In conclusion, we use Biot-Savart's law
to experiment and simulate bar magnets as a dipole.